This is the last class of this week. This class topic is displacement formulation and solution strategies. If you recall, where are we now is we discussed that depending on how the governing equations of elasticity are written, we can have two kinds of formulation. One is stress formulation, another one is displacement formulation. The stress formulation is discussed in the last class, where the equations are written in terms of stresses, and then another formulation where the same equation can be expressed in terms of displacements as well, and that is called displacement formulation, and we will be discussing that displacement formulation today. And once we discuss the displacement formulation, we will summarize all these equations that we developed so far, and then we see what are the different solution methodology, the techniques available, and from there we will choose some techniques and then proceed. Okay. So, whatever formulation we use, either displacement formulation or stress formulation, it is the same set of information are used, right. Same set of information means it is the same equilibrium equation, same compatibility equation, or strain displacement relation, or same constitutive relation. Now, if you recall, when we derive stress based formulation, then we equilibrium equation anyway we have to use. Equilibrium equation is, there is no other way, the equilibrium equation we have used. Then we used compatibility equation. You see, the compatibility equation and the strain displacement relation, they essentially tell you the same story, but in a different way. In this case, when we write the compatibility equation, here the displacement terms are completely eliminated. So, we use these equation when while deriving the equations in terms of stresses, and then in the constitutive relation we can have two form. One is the strain as a function of stress, and another is stress is expressed as a function of strain. We use this expression, right. So, these three equation when you combine, it gives us the equation in the stress form, and that was the stress formulation. Now, when we write the displacement formulation, equilibrium equation we have to use, this equation will be used. Now, since the equations are written in terms of displacement, we will not use the compatibility relation, because the displacement is completely eliminated. Instead, we use this equation, the strain displacement relation. But please note, it is the same set of information we are using, we are not compromising with the information. And then in constitutive relation, we will not use this expression, we will be using this expression. Okay. So, this and this together, these three equation will combine, and this gives us the equation which is in terms of displacement. Let us do that exercise. Since you will see, as we derive the displacement, deriving displacement formulation is relatively easier as compared to the stress formulation, and we will also see that in terms of solution, that is, even in terms of solution, this is relatively easier in terms of stress formulation. So, what we do is we will straight away derive this equation, of course using indicial notation for 3 dimension. We will not do this exercise for 2 dimension and then for 3 dimension, straight away we will derive it for 3 dimension, unlike we did in using stress formulation. Okay. So, as I said, these are the equations that we will be using. This is the equilibrium equation, and this is constitutive relation, and this is strain displacement relation. Please note one thing, it is implicitly assumed here that your stress tensor and strain tensor, they are symmetric, and that is why somewhere you will see that interchangeably I and J index are used. For instance, whenever we write sigma ij j and sigma iji, they essentially gives you the same set of information, same set of component. Similarly, here epsilon, it is written epsilon ji, you can correct it, you can make it ij, but essentially it is same, epsilon ij is equal to epsilon ji. Okay. So, first what we do is, first substitute this equation, this strain displacement relation, the equation number 1, this is equation number 1, sorry, this is equation number 1, equation number 2, and then this is equation number 3. So, first what we do is substitute equation number 3 into equation number 1. If we do that, then what will happen? Then you can parallelly do this exercise with me. So, sigma ij this becomes plus it is sigma ij comma j. This sorry, you substitute this equation in equation number 2, then this becomes, to start with, sigma ij, this is equal to lambda epsilon m. Epsilon m means I is equal to m, j is equal to m. So, this gives you half of u m comma m plus another u m comma m. U comma m means del u m by del x m. Okay. So, then we have lambda, then we have delta ij and plus 2 mu into half epsilon ij is this u I comma j plus u j comma I. So, this is your sigma ij. So, you can slightly simplify it. So, this becomes essentially lambda u m comma m delta ij and this becomes mu into u I j plus u j I. Okay. So, this is equal to sigma I j. So, this equation we have this. So, this is the combined equation when you combine the constitutive relation and the strain displacement relation. So, this equation we have. Now, next what we do is, next we substitute, this is the expression for sigma ij we have. Now, this expression of sigma ij, let us substitute in this expression, and if you do that, you try this, what the equation is, if you substitute this, then what we have is, let us try this. So, this becomes, so the equation is sigma I j comma j plus b I is equal to 0. So, this gives, if we have to differentiate the entire thing with respect to j, and if you do that, then becomes lambda u m comma m j delta I j, then plus mu, you have u I comma j j plus u j comma I j. Okay. Then plus b I, that is equal to 0. Now, let us slightly simplify this. You see here one thing you check, first you take this term mu into this term mu into u I j j, this becomes what? This becomes mu into u of I, that is j j. Okay. Then plus. Now, here check one thing. So, this becomes what? This becomes mu into u j comma I j plus. Now, here check one thing, this is delta I j, right, and this is true, this is delta I j is the Kronecker delta, and this is true when I is equal, this is 1 when I is equal to j, and in all other cases this becomes 0. So, in that case what we can do is, this becomes then lambda u m. So, j becomes I, then only, so if you expand it, you have some of the terms are non-zero and some of the terms are 0. The non-zero terms will be when I is equal to j. So, this becomes m I. okay, then plus b I is equal to 0. Okay. Now, we are almost done. So, this is mu u of I comma j j plus mu of, you see here is the j is the repeated index. So, j is now the dummy index, here m is also repeated index. So, m is dummy index, here also j is repeated index, the j is dummy index. So, now let us all these repeated index, the dummy index, let us write this as k. So, this is k. Okay. So, now k is the summation over k is equal to 1 to 3 and k is equal to 1 to 3, which is j j and k k are same. This becomes mu k u k comma I k. Again it is same because now k is the dummy index, then lambda u k comma k I plus b I is equal to 0. Now, then we are almost done. What we have now is, now let us write this. So, final expression will be this is equal to, so mu u of I k k plus, now if you check, if we take, since k I here I k and k I both can be interchanged as long as the u is continuously defined over the domain. So, you can take u k lambda plus mu common, and then this becomes u of k comma k I plus b I is equal to 0. So, this is the equation. Okay. You can derive these and please convince yourself. Now, so you see how many equations essentially we have. We have k k is a dummy index, I. So, essentially we have 3 equations. One is for I is equal to x, equation in x direction, I is equal to y, equation in y direction, and I is equal to z, equation in 3 directions. So, essentially we have total 3 number equations, and which is very logical, because when you are writing the equation in terms of displacement, only unknown displacement there are 3 unknown displacement in 3 directions. So, we have 3 unknown, but remember when we wrote the equation in terms of stresses, we had 6 equations, which is again very logical, because we have 6 stress components, 3 normal components and 3 shear components. So, we have 3 equations for stresses. Now, so you see one thing, please note, when you write this expression, when you derive this expression in initial notation, this derivation becomes very straightforward. You try yourself writing this expression, deriving this expression using all these differential operator and then you can see that the expression, the derivation is slightly tedious as compared to this. Now, once we have this, if I have to write this expression, this expression now written in initial notation. Now, let us write this expression in differential in operator term. Now, what is u I k k? When I write this, when you write u I k k, what exactly it means? It means del u I del x k del 2u del x k 2. Okay. It exactly means that. When you write u k comma I k, this means what? This means del 2 u k. U k is the kth component of u, either u x, u y, u z, that depends on what is the u, del x I and del x k, right. Now, so what you have essentially, now you remember what was your del 2 operator, this del 2 operator, if you remember that operator was del 2 del x 2, then plus del 2, if you take any function, any phi f, del 2 del x 2 plus del 2 del y 2 plus del 2 del z 2 of phi. Okay. That is the Laplacian operator. Okay. Now, if I substitute this, if I write this expression in terms of this del 2 and del operator, then eventually the expression becomes this. This expression becomes this. Okay. You try you please verify yourself. So, this is the first term, which was, this term was, if you recall, this term was mu into u I k k. This is the term, and then recall this term was lambda plus nu u I k. This term gives you this, and then plus b I. This was equal to 0. Now, if you combine this and write in a vector form, so u is essentially, now this gives you 3 equations. Okay. U is now u x, u y and u z. So, what term you are taking, depending on that you get first, second or third equations. So, this is the final equation written in displacement, written in terms of displacements. Okay. Now, once we have derived the equation in terms of stresses and then equation in terms of displacements, let us now summarize all these equations, and then from there we will see how that equations can be solved. Okay. Now, so finally, okay, finally this equation becomes this. If you this is the general form, and then if you write component wise, then these are the components in x, y, z direction you get, and these 3 are the equations. Okay. Please note here u v are the u v w are the components of u, where you write this u, now here it is u v w, this is the components. Okay. And all these u v w are the scalars, but here you can easily see it is written in bold letter. So, it is a vector. Okay. Now, so let us summarize these equations. What we have is, we started with, if you recall, we started with a very general form where we had 15 equations and 15 unknowns. And what are the 15 unknowns? We have 3 displacements, and then 6 strains, and then 6 stresses. These are 15 unknown. This is 3, this is 6, and this is 6, total 15 unknowns. And then we have 15 equations. 15 equations are what? The constitutive relations. We have 6 equation. This constitutive equation, we have 3 equations, and then not the equilibrium equation we have 3, then the constitutive equation we have 6, and then either you take strain displacement relation or a compatibility equation, we had 6 equation here, 6 equation here. So, either you take these 3 for stress formulation and these 3 for displacement formulation. So, total relations available is 15 relations available. So, this is for the very general form, but that these 15 cannot be really unknown, because we found there are some of the some relations can be again established between these equations, and we can combine them, and then we can reduce the number of equations, and that we did. Now, then we have stress formulation, and then stress formulation essentially what we did, we combined the equilibrium condition, the compatibility condition, and the constitutive relation, and eventually the equations we have is this, where sigma is the unknown and this is the equation available, and this is the final form of the equation written in terms of written in initial notations. And then we have another formulation displacement, where again the constitutive relation, equilibrium equation, and not the compatibility, rather the strain displacement relation is used, and we can have 3 unknowns and 3 equations. These 3 unknowns are the components of u, and this is the final form of the equation written in initial notation. Okay. So, either you use this form to, so then once we have any problem, either when we represent this, we have to represent this idealized system through some mathematical model, and this is the mathematical model written in terms of stress, and this is the mathematical model written in terms of displacements. Okay. Now, next see what are the ways to solve these equations. Now, you see again I will if you remember this is the same slide shown in one of the classes where we discuss what are the different steps we follow in any engineering analysis. We idealize the physical system and then write the mathematical model for the idealized system and then solve it. What we have done so far is in this week we try to write the mathematical model for an idealized system. Now, remember one thing, when we as we stated that time as well, every steps from physical system to idealization of the physical system, and then from idealization of the mathematical representation of the idealized system, and then again for the solution, every steps we make some assumptions. Okay. And these assumptions are very important because they are the limitation of any formulation. Now, when we write, so this is the general form of mathematical model, this is the general form we derived so far for linear elasticity problem. Now, from there you can write it in stress based form or displacement form, that does not matter, but this is the form, this is the mathematical representation of the idealized system that we have derived so far. And what are the major assumption we took? We assumed that that material is linear elastic material. So, therefore, we have essentially two constants, linear elastic and isotropic material, and then we assume that it is a small deformation theory, strains are small anyway, and that is the reason why this relation between the strain and displacement and the relation between strain and stress can be linear. So, these are the major assumptions that we had while deriving these equations, but again these assumptions are limitations of these equation as well, because there are problems where this linearity assumption cannot be may not hold, and in some cases, or there are problems where the elasticity assumption itself does not hold, material no longer remain elastic. So, in such problems these equations cannot be these equations we have to enrich this equation in order to incorporate all these features that the material exhibit when it undergoes deformation. Okay. Now, once we have this mathematical representation, next is the solution of this equation. Let us see what are the techniques that we have for the solution of these equations. Now, broadly these techniques can be classified majorly classified as analytical methods and numerical methods. There is another method called approximate method, but I am not putting it in a separate category. So, analytical methods is something where a closed form solution is available. Okay. For instance, if I have to if I give you any quadratic equation, for instance, if I give you the a x square plus b x plus c is equal to 0. Okay. Now, we know that the solution of this equation is equal to x, we can have the solution that is or we can have as a function of if you know a b c, then we can write what is the value of x from this expression. Even if we have some other expression, then for which we can solve the closed form. So, these solutions are obtained using is an analytically solved. Okay. Now, but there are problems, suppose the same equations which has, if I give you say a x to the power 5 plus b x cube plus c x to the power x square plus e to the power x is equal to 0. If I give you some equation like this, which you cannot have a closed form solution. In that case, what we have to do is we have to look for some numerical methods. Numerical methods, one very popular numerical methods for solving these nonlinear equations is Newton-Raphson method. So, similarly, when we solve elasticity problem, so depending on there are some problems where your boundary conditions are very simple, the domain itself is very regular. In those cases, the problem can be, the solution can be obtained through analytical method in a closed form way. But several problems, rather most of the problems exist that we encounter in real life, the analytical methods are not sufficient, and in that cases you have to go for numerical methods. Now, some of the analytical methods that can be used are power series method, then Fourier method, integral transform method, complex variable method. Now, in this class or in this course, we'll spend next 3 weeks, we'll spend mostly on power series method, how the power series method is used to solve these equations in different Cartesian coordinates and then polar coordinate system. And then one more week we will spend on complex variable method, this one and this one, that will be our emphasis on in this course. The numerical methods, for instance, these are some popular methods like finite difference method, finite element method. You must be having course on finite element method and finite difference method in your curriculum. Then we have boundary element method. Then there is another class of method which is different than finite element method, which do not rely on element, unlike finite element method, which is sometimes called as mesh free methods or element free method or particle methods. So, these are the some methods available, numerical methods. So, we will not discuss in detail all these methods. Now, here one point please note, you see the most of the problem or rather I would say all the problems that we really encounter in real life, that when you go to industry and then you even if it is elastic problem and you encounter a problem, then you will see that you have to use some numerical technique. The analytical methods are not feasible there. Okay. So, essentially for the practical purposes, numerical methods we have to use at the end of the day. But still we will be spending next 2 weeks and then another 1 week on complex variable approach. So, we will be spending 4 weeks on analytical methods. Okay. There is a very important reason for that. You see, let me give you an example before I state what I intend to say. Suppose this is the problem encountered in defense. Okay, we have, suppose you take any structure. Okay, either you take beam or plates. Okay, for instance, say take beam. We have a beam like this. Suppose you have a beam like this, and then which is subjected to some impact. Okay, impact by a projectile. Say when you fire, these bullets come from the gun, and that bullets hit any target, but that target could be a beam, that target could be a plate or any structure or wall. Suppose if it is a beam or a plate, take a clamped beam. Okay. Now, once these targets hits this structure, then what may happen is this structure may fail like this. This structure may fail like this, and this is the projectile. So, it breaks or it undergoes huge deformation. Okay. Now, one important term that is used in defense is the limit velocity. Limit velocity or ballistic limit. Okay. Now, what does it mean? It means, suppose in a very crude way, if I have to tell you, that suppose you have a structure, then you fire a bullet, and then the bullet has some velocity. For certain kind of bullet, the bullet has some velocity. Now, if the velocity is small, then what may happen? The target may not fail, the considerable deformation may take place, but it may not get penetrated. But if you keep on increasing the velocity of the bullet, what will happen? At some point of time, this target may break. Okay, the bullet may penetrate the target. Okay. And that is the limiting velocity. The velocity, at which it happens, that is the limit velocity. Okay, there are many other definitions of the ballistic limit, but this is one way we can say. So, that is the limit velocity. This is a very important measure to quantify the safety of a structure, okay, or the strength of a structure. Now, suppose you have to find out limit velocity of a structure. Okay. Now, any problem we solve, there are majorly three approaches. One is the experimental approach. You do experiment in lab and then find out the limit velocity. How do you have to do the experiment? You make a sample and then fire projectile, and you keep on firing projectile with different velocities, and then see with your all this camera and all this data acquisition system at what velocity the penetration takes place, and you say that this may be our limit velocity. Another approach is the numerical simulation, where you keep on simulating this the same thing, the same experiment, but you simulate in computer. You simulate this numerically simulate this entire event and keep on increasing the velocity, and then see at what velocity this penetrates, and this is your limit velocity. Now, suppose, but this is time consuming task, right. Now, suppose if you have to quickly assess what is the limit velocity, quickly, suppose in some reason you have to understand, you have a plate and you want to quickly assess that, okay, what is the limit velocity of a structure. There is a model, the analytical model, which tells you that if it's, I am just give you an example to tell you the importance of analytical model. Suppose this is the mass of this projectile is g, okay, and then which is limiting which the initial velocity of the projectile is vi. Vi is at what velocity that impact takes place, and once the penetration is done, then Vr is the residual velocity of the projectile. And suppose after the penetration, what happens is some chunk of the object from the target comes out, and suppose that suppose some chunk of the object comes out with the projectile, some chunk of the target comes out to the projectile. So, suppose this velocity, this mass is m, small m. Then it says there is an analytical method, which analytical formulation, which says that velocity, the critical velocity would be square root of V I square plus g by g plus m V r square. Okay. This is the critical velocity, this is minus. Okay. This is the critical velocity. Okay. Now, this expression was derived almost in 1963. Okay. Now, this is derived with a very simplistic assumption, but what is observed is this gives when your impact velocity is very close to the critical velocity, this gives a reasonable approximation of the limit velocity, which can be used not for the detailed study of the behavior of the structure, but for a quick estimation of the limit velocity. Now, why I gave this example, that reason is the exercise that we will be doing in next 3 weeks and also the another 1 week. If you look from industry perspective, that exercise you may not do in industry on a regular basis, but that exercise will give you a platform. If you have to develop an analytical model for some problem, for some physical process, this exercise will tell you what are the possible ways that you can adapt to come up with an analytical model for some physical process. And also, when we talk about complex variable method, from complex variable method we will try to solve some of the example, and that example will take us to a very fascinating branch of mechanics, which is called fracture mechanics, but that we will discuss. You do not have to bother right now for that. Whenever we come to complex variable method, we will discuss that there. Okay. So, now these are the things that we will be doing in the next 3 weeks, but before that few things is very important, two important things that is important, that is called first is Invariance Principle. Invariance Principle, if I exactly state it, what is written here in this what is written here. Now, allow me to read it, you can also read it. If the force acting on a small portion of the surface of an elastic body are replaced by another statically equivalent system, that is very important. You remember in mechanics you studied equivalent force coupled system, where the set of force is replaced by equivalent force couple. For instance, if I give you an example, suppose you have if I apply a load like this, you have a column or a tower or anything, okay, a post, and then if I have a load like this, and if this distance is E and this load is P, and this can be the equivalent system, could be like this. This is P and then moment P into E. Okay. So, this is called equivalent system. Okay. Now, what it is says that if it is statically equivalent system, if you replace the forces by a statically equivalent system of forces acting on the same portion of the surface, the redistribution of the loading produces substantial changes in the stress locally. When you come from this to this, what will happen, because of this a statically equivalent system, but what happens is, but because of this change, there will be change in stresses and deformation locally, but as you move from this place, it will be this effect will be very small. So, negligible effect on the stresses at a distance which are large in comparison with the linear dimension of the surface on which the forces are changed. Just to give you an example, if I have to give you an example, for instance, quickly, if I take, suppose again the same thing, suppose you apply a load like this, suppose this load is P. Okay. Now, suppose this distribution, now what you do is, suppose you take another problem where same thing, but the load is P by 2 and then another is P by 2, or you take another problem where here load is say 3 loads you apply, all are P by 3, P by 3. So, you see all these systems, system 1, system 2 and system 3, they are statically equivalent system. Okay. Now, what this invariance principle says is, now because of this application of the load, you have some stresses generated throughout the body, you have displacement throughout the body. Similarly, when you change this, it will also give you the stress distribution and the strain distribution throughout the body. This system will also give you some stress and strain distribution throughout the body. But what this principle says is, if you change this, then locally, if you take a point locally around this zone, okay, this is just this zone I am showing just for the representation, around this zone you may have some drastic change in the stress field or the strain field, but as you move further, suppose you consider another zone here, another zone here, another zone here, which is far away from this change, your effect will be very negligible. So, the distribution of stresses here, distribution of stresses here, and the distribution of stresses here, they will all be same. The effect is very negligible. Now, for the time being, you take it for granted, this invariance principle, you take it for granted. We will be solving one example like this. We have a plate with a central hole and which is subjected to in plane load, say sigma, and then we will compare this solution with a solution like this, sigma and then sigma. So, where there is no hole and there is a hole. So, it is essentially some some small changes you have in the problem, and then we will plot this distribution of stresses and then see if we move far away from this defect, from this change, will the distribution of the stress in both the problems almost same. Whereas, if you consider the distribution of stress and the displacement and the strain very near to this change, your these two are drastically different. That is what essentially this invariance principle said. We will try to demonstrate this. We will try to see whether it is actually happening or not, but for the time being you can take it for granted. Another important thing is that we will be using very often is the principle of superposition. The principle of superposition is something that you all know, and you probably that time you did not know there is a name called the principle of superposition. You learned it in your 10th standard or the 7th standard, when you actually first you were introduced to algebra. Now, what it says that suppose you have say a1 x is equal to b1, you have a set of linear equation like this, and then you have a2 x is equal to b2, and then you have a linear equation, set of linear equation like this. Suppose here the solution is x1 and here the solution is x2. Okay. Now, what the linear principle of superposition says that, now if you have a system called a1 plus a2 x is equal to b1 plus b2, then the solution will be x1 plus x2, and you see you all know this. So, this is equal to this will be is equal to this plus this. That is what linear superposition. Okay. Now, this is valid if your equations are linear. If the equations are non-linear, you cannot say that. Okay. Now, since the linearity is one of the very important assumption in our formulation, so this superposition is applicable. What it tells you in the context of, if I have to tell you this the same thing in terms of some example, suppose you have a system like this, you have a system like any arbitrary system, we have a load like this and like this. Okay. Now, you want to analyze it. Okay. Now, this can be equal to a system which is same system which is subjected to, we have 3 system, and then this system is subjected to load this subject is subjected to load this, and this system is subjected to load this. This plus this is equal to this. That is what linear superposition says. Okay. And we will be using this principle very often whenever we have different kinds of load acting on an object. We try to split into species and then combine them. Okay. Now, so with this we are almost ready to we have already set the platform, all the necessary information that we require to go further and apply to solve some problems in elasticity. We are almost ready for that. So, next week what we do is we will see how the boundary value problems that we have formulated, how to solve them. And the next class we introduce one of the very important concept next week, that is plane stress and plane strain problems. You remember we discussed that there is nothing like 2-dimensional problem in real life. All problems are 3-dimensional problem. Any object you take, this is essentially a 3-dimensional object, right? But under certain circumstances, we can idealize this object as 2-dimensional object, so that we can, our analysis become simpler. We have to deal with the less number of unknowns, we have to deal with less number of equations. We will see that what are the circumstances, what are the situation where the 3-dimensional problem can be projected, can be idealized, as two-dimensional problem, and what are the different kinds of such idealization, two idealization, one is plane stress and plane strain. We will discuss in detail in the next week. Okay, then I stop here today. See you in the next class. Thank you.